Okay, good morning. So what I'm going to try and do is show you the derivation we talked about last week. So the idea here is we have some function which we can draw here, which would be some mathematical function f of x. Now this could be, say, a cubic polynomial, it could be a sines, cosines, exponential. The actual form of the function is unimportant, so we write it as just a generic function f of x. And so the key premise of the finite element method is to approximate this function using a series of straight lines. You can go to higher order polynomials that you use to approximate this, but for now we're just going to use straight lines. And the idea here really is that we have the straight lines and they're connected at the point where they join. So the lines themselves we're going to call elements. These are our finite elements, and the points where they join are going to be called the nodes. So what we're going to do is we're going to number these. We'll have this one as 0, this is the origin. This one is located, so our bottom axis is the x-axis, our top axis, we're going to say sum f of x. Actually, just to make the notation consistent with what we did last time, we'll make the function u of x. So one of the things to be aware of is the finite element method is used for a variety of different types of modelling. So we could use it, say, for u, which could be a displacement, could be a velocity in fluid dynamics. We could use it for t, which could be a temperature. Generally what we find, and hopefully you kind of got a feel for this last week, is that most of the equations are the same. We have the same concepts, things like second order derivatives that are kind of diffusive terms. Those could be diffusion of fluid flow, could be diffusion of stress, it could be diffusion of temperature. So when we start talking about these equations, when we solve these equations, please bear in mind these are general purpose methodologies that can be used for a variety of problems. So when we talk about the different functions, we'll try to mix up the notation just to kind of emphasize that. But in principle, it's just algebra. The process is exactly the same to solve and understand these. Okay. So essentially what we have is a series of points on the x-axis. Just for completeness, let's make this go through 0. So we have x0, x1, x2 and x3. So you can think of these as just numerical values. So the one at the origin would be just equal to 0. This one here we can say is just equal to 1, 2 and 3 if you like. But just to make this general, because later on, we may not just want to have 0, 1, 2 and 3, we want to go to kind of arbitrary numbers. We use basically algebraic expressions for those. And so for the value of u at various points, we're going to call this u1, this u2, this u3, just this u0. So the way this works is we have our function u of x, and basically for that function, one second, u of x when x is equal to, say, x1, we're going to define to be u1 and so on. So u at x is equal to x2 is just going to be u2 and so on. So this is just notation. So the value of u as a function of x at the point x1 or x2 is just u1 or u2 respectively. Okay, so essentially what we want to do is we want to take one of these linear elements, it's just a straight line between a point u1 and u2, where the x value we know is just x1 and x2. And what we want to do is we want to define a straight line that fulfills those conditions. So we call this u element, so it's a straight line. The straight line is the element, so essentially u of element is our notation. We're saying u element of x is going to be of the form mx plus c. So it's just the equation for a straight line. So essentially we're trying to derive a straight line that fits between those 2 points. And this is all because the idea is we're going to basically derive a series of straight lines that approximate this function. So this is just one line, but once we've got this one line in a general form, we can use exactly the same process to get every single one of these bits of line. And by ensuring that they always go between, say, u1 and u2, or between u2 and u3, we ensure that we have a function that is what's called continuous, or at least piecewise continuous. That is, the endpoints of the two elements joined together. Okay, so let's take that expression for the straight line, and what we're going to do is we're going to substitute in the two known values. So u element at x is equal to x1, we know is equal to u1, which we know is equal to m x1 plus c. So all we're doing is we're substituting in the fact that we know at u1 the value of x is x1 for that equation. We can do exactly the same thing at x is equal to x2, and that gives us u2 is equal to m x2 plus c. So essentially you have now two simultaneous equations where the unknown values are m and c. And the idea is we want to solve, in order to get m and c, that gives us this straight line. So the process here is simultaneous equations. Various ways you can do this, but probably the simplest is to take one equation away from the other. And in doing that we get u2 minus u1 is equal to m x2 minus m x1 plus c minus c. So you can see the two c's are going to cancel, and we're left with an equation with just one unknown, which is m. So the process now is we rearrange this, we take out m as a common factor, and we divide both sides by m. So what we end up with is u2 minus u1 is equal to m x2 minus x1, and so then we rearrange to say m is equal to u2 minus u1 over x2 minus x1. Okay? So now we know this value of m, we can substitute that back into one of the two equations, either a or b. So I'm going to substitute into equation a. So equation a we can just about see there at the top. So what we're going to do is we have u1 is equal to brackets, so we're just putting in the value of u2 that we know. This is times x1 plus c. So you can see now we have an equation here where the only unknown value, the only thing we need to determine is c. So now it becomes a case of just rearranging in order to get the value of c. So we can rewrite this as c on one side, and we're going to have u1, and we're moving this expression in terms of x1 to the other side. So we have a minus sign, and that becomes u2 minus u1 over x2 minus x1, x1. Okay, so the next step is to get a common denominator for both those expressions, just so we can re-express both terms in the equation in a nice form. So we have x2 minus x1 here, minus u2 x1 minus u1 x1, and now everything is over x2 minus x1. So all we've done here is we're basically taking this common denominator here, and we multiplied u1 by it, and then we just multiplied out the bracket on the right here to give these two expressions here. Okay, so then essentially now we just have to rearrange and collect terms and see what cancels. So if you look, you can see that we have u1 x1 on both sides of the equation. So there's a mistake here. When I multiplied out the brackets, this should be a plus, because we actually have u2 times x1 and then minus u1 minus the x plus. So what we see now is that the x1 term here and here will cancel out. So this term and this term will both cancel out. And what we're left with is u1 x2 minus u2 x1 over x2 minus x1. Okay? So that's our expression for c. So this is just purely algebra. Hopefully this makes sense. If any of this is unclear, please try working through yourself and ask me any questions. And with all of these things, it's just practice. So, you know, this for people who've done any algebra recently will be trivial. If it's been 5 years since you've actually done any of this, then it just takes practice. It's just one of those things you keep doing, and eventually it gets easier and easier. Okay, so now we have our equations here for a general element, U element here. And what we want to do is basically just substitute these values of m and c that we now know into that equation. So I'm going to just do that down the bottom here. So the equation for u element as a function of x is equal to the expression for m that we know is from before is u2 minus u1 over x2 minus x1 x plus the expression for c we've just derived there, which is u1 x2 minus u2 x1 all over x2 minus x1. Okay? So then the last step, what we're going to do is we're going to rearrange this and collect the terms for u1 and u2 to get an expression essentially for the element just in those 2 points. Now the reason for doing this may not initially appear clear, but in doing this we actually get what are called interpolation functions, and we get a much nicer form. So luckily we've got the same common denominator on both, x2 minus x1, so we don't have to do anything with that. Essentially what we do is just multiply out, we get u2x minus u1x plus u1x2 minus u2x1. This is all over x2 minus x1. And then we just collect together the terms. So we have essentially u1 brackets x2 minus x all over x2 minus x1 plus u2 x minus x1 all over x2 minus x1. So it's a little bit sloppy, let me just clean that up. Okay, so these are what we call our interpolation functions. This is n1 and this is n2. Okay, perfect. So that then gives us, just finally, an expression for u as an element of x as n1, which is a function of x, u1 plus u2 n2, which is a function of x. So although it may not appear like we've done too much, one key thing to note here is that now our line as a function of x, all of the x dependency has been collected in these interpolation functions, and then we just have the values at the nodes. So we now have an expression where all of the x dependency is in n1 and n2, our interpolation functions. And this is really key to the finite element method, as I'll explain in the next